real gun that weighs less than your phone, fires live ammunition, and somehow still works. This isn't a gimmick or a prop. It's a mechanical experiment pushed to the edge of physics. This is the ounce pistol. If precision engineering at its limits fascinates you, subscribe now, because this story isn't about firepower. It's about how machines survive. Every firearm ever built begins with a question. Usually that question revolves around power, range, reliability, or control. Designers ask how fast a weapon can fire, how accurately it can hit, or how long it can survive harsh conditions. The ounce pistol begins with a question that ignores all of that. How small can a real gun be before it stops functioning as a gun at all? That question is not theoretical. It cuts directly into the foundations of mechanical engineering. When a system is scaled down, the properties designers normally rely on begin to disappear. Mass fades away. Inertia collapses. Heat concentrates instead of dispersing. Tolerances tighten until they no longer forgive mistakes. A mechanism that feels effortless at normal size becomes fragile and unstable when reduced too far. The ounce pistol exists precisely inside that unstable space. It does not sit comfortably within the rules that govern normal firearms. It lives where those rules begin to fail, where the margins designers depend on shrink until they almost vanish. That is what makes it dangerous to design, difficult to execute, and fascinating to study. At first glance, it barely resembles a firearm. It is shorter than most pocket knives, thicker than it is long, and light enough to vanish in the palm of a hand. There is no slide towering above a frame, no grip shaped for comfort, no sights, no magazine well, no ergonomic concessions. Everything that exists primarily to help a shooter has been removed. What remains is the minimum structure required for a firearm to function: a chamber, a firing pin, a trigger, a path for pressure to escape forward instead of backward. Nothing more. The ounce pistol typically chambers a .22 rimfire cartridge, often a .22 short or similarly low-pressure load. This choice is not about tradition or convenience. It is about physics. Rimfire ammunition allows the firing system to be extremely small. The primer is embedded in the rim, eliminating the need for a heavy centerfire firing pin and complex impact geometry. Chamber pressures remain low enough that ultra-thin walls can still contain them safely, provided the tolerances and metallurgy are precise. At this scale, precise does not mean accurate within fractions of a millimeter. It means accurate enough that failure never has the chance to begin. There is no room for wear to be absorbed, no extra strength to compensate for mistakes, and no redundancy to hide flaws. Reliability here comes not from durability, but from exactness. Building a large gun is comparatively easy. Add mass and recoil slows down. Add length and pressure spreads out. Add buffers and springs, and the system becomes forgiving. Problems still exist, but they are softened by scale. Designers can rely on inertia to smooth timing and absorb error. Scaling a gun down does the opposite. Recoil becomes immediate instead of gradual. Heat spikes sharply instead of spreading out. Any friction becomes significant. Any misalignment becomes catastrophic. At this scale, physics stops being cooperative and starts becoming aggressive, turning minor imperfections into immediate failure points rather than long-term wear. The ounce pistol survives by refusing to fight these forces. There is no blowback system, no recoil operation, no delayed unlocking. The barrel is fixed permanently. The chamber remains closed during firing. When the trigger is pressed, the firing pin strikes the rim. Ignition occurs, pressure pushes the bullet forward, and the empty case stays fully supported. Nothing cycles, nothing unlocks, nothing moves afterward except heat and vibration. That simplicity is not a limitation. It is the only reason the design exists at all, because introducing motion at this scale would demand mass, timing margins, and structural tolerance the concept simply cannot afford. Introducing a moving slide would require mass. That mass would demand stronger springs. Stronger springs would need longer travel. Longer travel would increase size. The entire premise would collapse under its own requirements. So the ounce pistol accepts limitation instead of fighting it, choosing mechanical honesty over forced solutions that would undermine the concept itself. The firing pin system is brutally direct. There is no leverage to soften the trigger pull. The trigger directly compresses the firing pin spring with almost no mechanical advantage. The pull feels stiff relative to the size of the gun, but that stiffness is deliberate. A lighter pull would require additional components or longer movement, both of which introduce new failure points and additional complexity. At this scale, simplicity is not elegance, it is survival. Every part that exists does so because removing it would cause the system to fail. There is no redundancy, there is no backup. There is only correctness, enforced by physics rather than design philosophy. Heat is the next problem that refuses to scale down. In a conventional firearm, heat spreads across barrel length, slide mass, and frame volume. In the ounce pistol, there is nowhere for it to go. After a single shot, the chamber temperature rises sharply. Fire again too quickly, and material properties begin to change, sometimes within seconds rather than minutes. Metal expands. Tolerances tighten. Structural margins disappear. At this size, even slight thermal expansion can alter alignment enough to cause malfunctions or unsafe conditions. The gun approaches failure not through wear, but through physics acting faster than the materials can respond, leaving no time for gradual degradation or warning signs. This is why the ounce pistol is not meant for sustained firing. It is a proof of concept rather than a service weapon. Engineers designed it knowing exactly where the limits were, and they stopped just short of crossing them. Functionality exists, but endurance does not, and that trade-off is intentional. Material selection becomes critical when every gram matters. Steel is used only where absolutely necessary, primarily around the chamber where pressure must be contained. Everywhere else, material exists solely to maintain alignment and structural integrity. Decorative finishes are irrelevant. Excess thickness is unacceptable. Every added fraction of mass must justify its existence through function alone. Even surface treatments are chosen carefully because additional material changes mass distribution and thermal behavior. When a component is this small, coating thickness is no longer cosmetic. It is structural, capable of altering clearances and heat flow in ways that larger systems would never notice. This is why the ounce pistol feels closer to a precision instrument than a weapon. It has more in common with mechanical watches or micro-machined tools than with duty pistols. Assembly matters. Orientation matters. Alignment matters. There is no tolerance for sloppy construction because at this scale, mistakes do not shrink. Consequences grow. Handling the ounce pistol makes its priorities immediately clear. It does not sit comfortably in the hand. It offers no intuitive grip. It makes no effort to accommodate the shooter. This is not a design failure. It is a design choice, made deliberately to preserve mechanical integrity over human comfort. The human interface was never the focus. The experiment was mechanical, not ergonomic, and any attempt to improve handling would have required compromises the design could not afford. As a result, the pistol is profoundly impractical. It is difficult to aim, difficult to reload, difficult to fire comfortably. It offers minimal ballistic performance and no sustained capability. As a defensive tool, it makes little sense. As a duty weapon, it makes none at all. Judging it by those standards misses the point entirely because usefulness was never the goal. Demonstrating what happens when design is pushed to its limits was. The ounce pistol exists to expose assumptions. Modern firearms rely on mass, leverage, and timing margins that designers rarely question. Slides slow recoil, frames absorb heat, springs can be tuned. The ounce pistol removes those assumptions and forces designers to confront what actually makes a firearm function. Ignition, containment, alignment, timing, nothing else matters. That is why engineers respect it. Not because they want to use one, but because it demonstrates discipline. It shows restraint. It shows an understanding of when to stop. There is no cheating here, no hidden buffers, no disguised mass. The gun works because the math works. Historically, firearms evolved toward higher capacity, better control, and increased survivability. The ounce pistol moves deliberately in the opposite direction, not to regress, but to explore the boundary. It defines the edge by existing just inside it. What remains is not comfortable, not powerful, but it is honest. And honesty in engineering matters. Every system has limits. Pushing toward those limits teaches lessons that safe designs never reveal. The ounce pistol teaches those lessons in metal, heat, and pressure. It proves that guns are simple machines only when size allows forgiveness. When forgiveness disappears, mastery becomes mandatory. The ounce pistol is not impressive because it is dangerous. It is impressive because it survives. It fires. It does exactly what it was designed to do, and nothing more. If you love precision pushed to absurd extremes, subscribe, and I'll see you in the next breakdown.